Teamworking skills. I wanted to talk about how do technical software people manage to work together to create software as a team of people. There are specific technical skills that are required. In particular, this means methods of scheduling work. How do you allocate work to yourself and to other people and do things in the right order? It means coding together. How do you ensure that your code fits together with code that other people are writing? And it means, how do we share information? How do we make sure that every member of the team knows the things they need to know, but without wasting their time knowing things that they don't need to know? Scheduling work is a major part of managing both yourself and other people. Before you can manage other people, you first need to know how to manage yourself. Don't even try to manage other people if you can't manage yourself. Time management is a technical skill. It is not part of your personality. It's not something that some people are just inherently good or bad at. It is a technical skill that can be learned and taught. And there are specific technical and management tools to use to do that. Don't confuse the skill of time management with the particular choices of task priorities that are plugged into it. I am sometimes accused of poor time management, including quite recently by some of my own managers. I actually think I'm quite good at time management. I'm going to show you the kind of time management that I run in my own projects. I'm going to show you some of the mathematical models that I've researched and published on in this area. And I teach time management like this. So I think I'm actually quite good at time management. Sometimes you will get a mediocre manager who comes in and accuses you of bad time management because you haven't prioritized X, where X is typically something that they want, not your own priority. So time management doesn't mean prioritizing anything in particular. Time management is the skill of handling multiple demands on your time with different priorities. So it would be fair game to criticize me for not prioritizing your thing, the email that you sent me 3 weeks ago that is really important for you. But if it's not my priority, I can be doing really good internal time management while still not delivering the thing that you happen to want. The reason we need to do scheduling then is that modern life, for better or for worse, tends to throw many tasks at us at the same time. Most human beings quite like having a single task that they can focus on. And if you just tell someone what to do and then what to do next, it's very easy to do those things. Any job that software people work on is not going to have that structure. It's going to constantly have multiple demands on our time. We will have many tasks coming in. Every task effectively has a priority. Each task has some initial estimate of how long it's going to take. It has a probability of its duration. And these tasks almost always fragment. They will split, typically for two reasons. A task can split into multiple subtasks as you study it and understand it some more. So someone might ask you to write a GIS system for the robot, and when you sit down and think about it, you're going to split that into, find a library, learn to use the GIS library, implement your code, test it, so on. That's splitting a task into subcomponents. Tasks will also tend to spawn additional tasks. As you work on something, that gives you ideas. It gives the people around you ideas too for additional tasks that can be added to your set of things to do. So you will typically find this branching structure, all the things you're going to do. If you like mind maps, like my lecture notes here, this is often a great way to think about all the things you're supposed to be doing and put them into some kind of structure. The problem is they have this branching structure and you are a serial computer. You can only do one thing at once. The whole aim of this game is to serialize stuff from that branching hierarchical structure into a series of things with the correct priorities to get them done. All of this stuff changes, as with everything in software creation. It all changes as you go along. So as you start doing a piece of work, you will learn more about what's involved in it. That will give you both different estimates for how long it's going to take. It will also give you different estimates of what all the subtasks actually are, and it may also affect your priorities or your team's priorities. You might learn that something is going to be a lot more useful than you thought it was going to be, because you start doing it and it gives you an idea for a new application and a new bunch of customers and all this extra stuff that is going to increase the priority of that task. So this isn't just an innate natural talent certain people have. There are mathematical optimal algorithms for doing this correctly, for doing it optimally, called scheduling algorithms. So where have you already seen this? You've already studied these. Operating systems, spot on, right? This is exactly what you have already studied in your operating system class. You've got a bunch of tasks coming in, they've got priorities, they've got durations. Your task is to run a scheduling algorithm, serialize them, get them done in the best possible order. Brilliant. Process management for CPU, FIFO, etc. Spot on. So here's how not to schedule tasks. This is the bad old days of the waterfall Gantt style approach. So here you sit down at the beginning of your project and you completely fabricate a bunch of expected durations for each of these tasks. You assume that you know all the tasks in advance, that you know everything about how the project's going to run. There's a great one of these floating around the net for it's sending up Albert Einstein submitting a project proposal for discovering relativity, and he's got, month 17, I will work on the tensor equations, and in month 18 I will find the problem with the tensor equations, and in month 19 I'm going to fix it using a Christoffel symbol. This is funny because obviously that is a research project and you don't know in advance what are all these things that are going to happen. The whole point of doing a research project is to learn as you go along, and what you learn is going to update all your plans and everything you know and everything you're going to do. Every software project is a kind of research project. If you already knew how the thing was going to be designed, you wouldn't have to do any work. You could just start with a blank screen and write out the program from the first line and the second line and so on, because you'd already know what the program was. What you're trying to do here is discover what the program is, and that is a research process. Even for developing a very utilitarian piece of software like a web server, even something that's done before, you are still going through a personal research process, even if the world already knows how to do this. So you don't really know any of this in advance. You don't know what the tasks are going to be. You don't know what their durations are. In a student project, you don't deal with cost. This is the other major variable that comes up in real world projects. For example, if you're building robots, then every one of these tasks is going to have a budget associated with it. And you don't really know what the priorities are in advance. Something might come along that you decide to turn into the main product that you had no idea about before. So all software project Gantt charts are useless, made up lies. We should not be doing this anymore. Everybody knows that. I get really sick of seeing these in student projects because you know they're lies and I know they're lies. We have much better ways of scheduling work now. So there are other reasons for drawing this kind of figure. This is called a Gantt chart. Gantt is not in capital letters because it's a person. It's named after a Mr. Henry Gantt, I think, who invented them, management consultant. There's nothing inherently wrong just with drawing some rectangles on a piece of paper and saying the rectangles represent things that might happen at points in time. What is wrong is when you present this as a fixed upfront plan and promise this is what we're actually going to do. So times when you might actually use this kind of figure, a Gantt chart, rather than as a project plan, you might, for example, use it as a snapshot. You might say, we know there's all this uncertainty. This is what's called a maximum a posteriori belief. We're saying this is what we currently believe at this moment in time is the most probable state of the future world, according to what we currently know. But with the huge caveat that in 5 minutes time, I may well get an email that's going to completely update the plan. So you might want to obtain one of these as what's called a living document, something that changes even on a minute by minute basis as new information is coming in. Or you might want to draw pictures like this as a record of work that has been done in the past. When work moves into the past, it is completed, then you know what actually happened. And if you ever need to explain to someone else what work was actually done, it's a nice way of presenting it. But they're absolutely useless as a way of promising what you will actually do in the future, because you have no idea what's going to happen in the future. So a much better way to schedule work in software world is to use what is called a dependency diagram. So here we have our current picture of all the tasks we know about. I've colored the ones that have been done in green, ones that are in progress in yellow, ones that are to do in the future in blue. Red is tasks that are waiting. That can be something that's delayed because it's waiting for something outside. Maybe we have tasks that are optional. We call those ideas. They don't have to be delivered as part of the project. And we can draw arrows between them, showing what depends on what. So you can't start task A unless you've done the start task. You can't start task D until you've done the A task. So it's usually realistic in a software project to have some rough overall picture like this of roughly what's going to be done and what depends on what. But this is not promising anything about the order the work will be done in. It's not promising anything about the times things will be done in. And it's done with the intention, again, that this is a living document. This is going to get updated every time we get a new email. Someone might remove a task or add a task. So this is a snapshot of what's going on this week. This is what the project looks like this week, and we expect it to evolve every week. Formally, in computer science, this structure is known as a directed acyclic graph. So directed means there are arrows between the nodes. They have an order. So they have a direction. They define what is called a partial ordering. So a partial ordering means there are some limitations on which tasks can go before other tasks. So for example, you could never do task G before task B due to the arrows. So what you'll find, if you begin with the letters A, B, C through to H, if you didn't know anything else about the task, if you didn't know anything else about the dependency structure, you could imagine, how many letters are there here? 1, 2, 3, 4, 5, 6, 7, 8. You can imagine 8 factorial different worlds in which the tasks are all getting done in different orderings. Okay, that's a lot of possible worlds, a lot of possible orderings. The arrows here constrain which of those worlds are actually possible. So rather than having 8 factorial, you might have some, maybe 1% of those worlds are actually feasible. So you could have a world where you do the project in the order A, B, C, D, or you could do A, C, B, D, or you could do A, D, E, but you couldn't have a world where you do task G first and then A and then D. So partial ordering means we're restricting the set of sequences that could be performed out of these tasks. So each of these tasks has a status. It's either done, it's in progress, it's to do, it's waiting, it's an idea, and so on. These can be given formal representations in your IT management systems. You could have an enum representing each of these. And typically the structure of this is going to be a branching tree. Again, a task, you may find that it breaks down into smaller pieces, or you may find that it inspires a bunch of new ideas that get added to the project, especially if you're doing research style projects, as in universities. Is Charles muted? No, I'm not muted. Can you hear me? Can anyone hear me? Yes, okay. Your problem with your speakers, I'm afraid. Okay, so even in a non-research project, in a pure development project, you're going to learn as you go along. You're going to have ideas, typically ideas for new features that are going to get added into the mix. In a student project, typically you'll come and meet your supervisor every couple of weeks. We'll look at the plan, we'll review it, we'll add tasks, we'll remove tasks. We'll use this as the basis of our discussions to see how the project is getting along. So there's nothing here about how long each task is going to take, because you don't know, and we're being honest about that in this approach. So if we're given a dependency diagram, we have to serialize this. We have to compile it down into an actual sequence the tasks are going to get done in. Where have we seen this kind of algorithm before? Where have we seen this exact same figure in one of my lectures before, and this same process? Anyone? Pipelines, yeah, specifically out of order execution, right? Out of order execution is like pipelines on steroids, where you take each line of code and you figure out where are its dependencies. So again, there are proper mathematical optimization algorithms for doing all of this. If we run one of those algorithms, then we will typically end up with what is called a priority queue. So this is a serialized, it's a sequence of the tasks. This is your actual plan for what you're going to do. Also known as a to-do list or issues log or a Kanban in trendy agile programming world. So here we're going to consider the priorities of the tasks. You might compute this manually, you might have an automated system for doing it. This is part of my actual priority queue. This is what I use to plan my own life in Blinken. These are all the projects I'm involved in this week. These are all the things I need to do. So that included writing this lecture, writing a talk for my new third-year module on logic and computation, reviewing a paper. This is a big robotics project, building a new agricultural robot. So I don't do this completely automatically. I use these formal systems so that I can run Python scripts to extract certain things. I use a formal system of to do and done and wait and so on. I use a bit of manual subjectivity to move things around. I actually just keep all this in a big text file and I edit it in Vim. Vim folding mode is very useful here. Vim outliner mode is very useful here. Git is very useful because you can store the history of this. So you always have a record of how your project was evolving over time. Remember that the order that you execute these tasks in is not fixed in advance. It's going to depend on a bunch of things, specifically your mood. Sometimes you wake up and you're in a very analytic mood. Sometimes you're in a creative mood. Sometimes you're in an administrative mood, which means you're not feeling analytic or creative. So you're going to do some administration instead. Maybe these are affected by things like the weather, your social life, complex psychological factors. As far as project planning is concerned, it's random. So people are going to wake up on different days and feel like doing different kinds of tasks, and the plan has to be able to account for that. When you do task planning at scale, you will typically be getting bombarded by requests. Currently still by email, maybe by other systems like instant messaging. Maybe people knocking on your door. People will come and ask you to do other things, and it's important to distinguish the form of those messages from their content. So this is a system that I at least try to use. You might have come across it. It's called Getting Things Done. Everyone calls it GTD, from David Allen. Lots of academics use this, especially here in Lincoln. This is specifically an email triage system. The triage is like what they use in hospitals, where patients come in and you decide what to do with them. Are they so important you have to do it now and send them to the emergency room? Do you send them home? And so on. This is the reason you will notice different delays in the emails you send to academics. There is no point usually in asking an academic, did you get my email? If they're running this system, they will have got your email. It will be triaged and it will have been put in the correct place for it to be processed at the correct time. So fundamentally, when an email comes in Getting Things Done, you take a look at the title. You don't always have to open the email to do this. You say, is it actionable? Is this something I need to do, or is it information? If it's information, then you move it and you put it in an information folder somewhere. Or if it's junk, you throw it away. If it is actionable, you say, can I do it in less than 2 minutes? In which case you do it, because it's quicker just to do it than to faff around with all the other systems. If it's going to take longer than 2 minutes, then you need to think about where it goes. If it's project work, you normally put it in a dedicated project system to keep track of everything in each project. Often in real life, you're working on multiple projects at the same time, so you've got a whole bunch of these. You need to think, what is the next action? Is this an action that I'm going to do? Is it something one of my people are going to do? If it's one of my people, I'm going to delegate it. This is a formal process. You can do it by email using the forward button. You can do it verbally. But if you're tracking this on an IT system, you have to formally record that this task has been delegated to someone else. When you delegate to someone else, the task goes on your wait list. So remember, some of the tasks on my to-do list were marked as wait. That means I'm waiting for someone else to do something. And my work on that project is blocked until the wait task has been done. If it's a task for me, then I can put it in a scheduling system. Then it will actually go into my to-do list. Maybe it has a deadline. Maybe that stuff gets linked into my calendar. The deadlines will be set according to the priorities of those tasks. So, for example, if you're an academic, you're receiving 200 emails a day, typically. You have to be very quick and get all these things in the right places. Emails will be triaged, sent to the right place, and responded to at the right time. Now, a key part of this is don't use the email system itself to manage tasks. An email is not a task. An email is a written sequence of ASCII characters. It is a medium. The task is the message which is being transmitted through that medium. And if you confuse the two, you can get yourself into a mess. There are some people who try to do all their task management using their email inbox, which is usually a really bad idea, because you're mixing up things that are tasks and requests and delegations and information, and it's all sitting there in a big mess. You need to formalize it and put everything in the right place. That means when a request for you to make an action comes in, you have to take that out of your email system and you put it into your task management system. In particular, nowadays, these requests don't just come by email. They might be coming through instant messaging or from phone calls or people just coming to knock at your door. And you don't want to have that stuff mixed up with your email message transmission system. Yeah, managing email is a huge activity. There's a lot of email in the world, Gary. Learning to manage it is a major part of the software development process. Okay. So that's an overview of scheduling your own time, your own tasks. When we go beyond that to larger projects, as you gain more experience, you may be given some management authority to schedule other people's time in addition to your own. So learn to do this stuff for yourself first. We're going to schedule other people's time using the same idea. We've got the same dependency diagram. Here's all the stuff that needs doing. We know what depends on what. But this time we have the ability to compile it down into a set of parallel to-do lists for all the team members. So where do we study this before? Again, you've had this in my lecture. Okay, so this is parallel computation. This is how you take a dependency diagram and you figure out what's the most efficient way to parallelize a bunch of work. So, for example, you might have multiple CPU processors, you might have GPU processors. We already know how to do this. We've already studied the mathematical models for how to do this properly. So here's an example of that process for the project I'm working on right now. This is called the ORWAC project. Here we're building a robot. This robot is called Teresa because it runs through fields of wheat. It looks for weeds growing in the wheat and it destroys the weeds without destroying the crop. So this is a pretty complex project. I'm the principal investigator on this. The budget is about £500,000. There's about 8 people involved in varying capacities. There's mechanical work going on building the robot. There's machine vision and AI. There's a lot of business and management and patenting processes, and all these things are happening in parallel. So we can take that dependency diagram and now we compile it down into a priority queue for multiple people. So I can see this is what I'm actually doing on the project right now. I'm writing a paper, I'm building a simulation, I've got a bunch of things to do after that. This is Dom, my postdoc. Some of you have met. He's been sitting in some of these lectures. He's working on the machine vision stuff, GPU computing, TensorFlow. We've got business tasks going on. We've got agricultural tasks of actually preparing the fields and building greenhouses and all kinds of things. But you can see this is a formal system. Each of these things exists as a tagged task, and that's something that can be analyzed by IT systems and optimized. When you create these tasks for other people, it's very important to understand the interface between your work and their work. Effectively, you have a big task list. There's too much work for you to do, and so you are going to take some pieces of your list and you're going to delegate them to other people. So we have to make it clear what we are actually delegating. A task on that list is just a few words of English, but it represents a big idea, a big concept. We have to explain to someone else what is actually wanted as part of the delegation. So it's important that we specify not the process, but what is called the deliverable or the end result. You should never tell someone how the work must be done. Always tell people what is the result. What do you need to come back with next week? If you're doing software development, one good way of doing this is often passing tests. If you specify the tests, you ask your delegate to make sure the system passes the tests next week. That's a nice quantitative method. How many of these tests have you delivered over that week? So we don't specify the method. This is called micromanagement, and it is very bad, and you will annoy people. You will get things done very inefficiently. Your staff will leave generally bad. You might recommend a method to use. You might suggest something, but never enforce it. You give the deliverable, and then it's up to them to solve the problem however they think is best. So especially in academia, a big part of management is teaching people about methods as well. But remember that teaching is a different activity from actually doing the work and delivering the project. So if I delegate the creation of my GIS database for the robot to one of my PhD students, say, I might have a meeting with them where I spend an hour teaching them how a particular Python GIS database works. That's good for their career development. It's going to give them nice tools to use, and they may wish to use it to complete the task I've given them. But I'm never going to tell them that they must use that tool to solve the task. I'm only going to tell them what is required as the output of the task. That's the interface. It's up to them how to implement it. Question from Gary. Is it dangerous to not specify a method in order to keep control? Code may significantly be changed if you don't specify some boundaries. Yeah, okay. So if there's something that I do need to specify, then I'll include that as part of the deliverable. So if I need you to build this database in a way that will be compatible with my function calls, I'll tell you what those function calls are. They're probably going to be Python function calls, but I shouldn't care if you then go and implement that in a Rust implementation, as long as you respect the Python API sitting up above it. If I really want you to deliver some Python code, then I'll make that part of the deliverable. I won't make it part of the method. If there is some reason why this really has to be in Python, I'll say your deliverable is you come back next Thursday with a Python program that makes the database work. But I'm not going to say come back with a working database and you have to do it using Python. It's a subtle difference, but it's important. Okay, cool. Okay, so other things you have to specify. This is typically done in an in-person one-to-one meeting, not in a team meeting, in a meeting with the person you are delegating work to. You're going to tell them what is the deadline. Often that is next week's meeting, if you meet each of your people once a week. In a real project, you often have to specify the budget. If you're doing robotics, this is going to involve trusting your person with substantial amounts of money for buying motors and batteries and things. Specify the reward for being under budget. If I say, here's £2,000, go and build a robot, what are you actually going to do? Are you going to be motivated to go and save loads of money and only spend £1,000 on building the same robot, or are you going to go and buy the first one that you find to save time and spend the whole of the £2,000? It depends on how you're motivated to do that. So if I say, here's £2,000, go and build a robot and keep the change, that's going to make you very motivated to look for cost savings. If I say, here's a budget of up to £2,000 and anything you don't spend, you just have to give back to me, then you're going to be much less motivated to go out and look for cost savings. So specify the reward for managing budget. You very importantly need to explain the value, the utility of the task. So as we saw in individual task management, most people have a constantly changing set of tasks. They're all maintaining their own task management systems, their own dependency diagrams. And for that to work, they need to understand the utility of each task coming in. So if your work is really important, you have to explain that, explain why it's important. Ideally, what is the ultimate cash value of the work, so that they know if something else comes along, if someone else asks them to do something, where should these things sit in their own priority stack. And then finally, it's important to explain about exceptions. How and when should a staff member raise an exception? This is just the same concept as exceptions in code. Code exceptions are based on this management concept, which came first. So a management exception means a junior staff member has encountered an unexpected situation and they're stuck and they don't know what to do. Should they try and figure out a solution by themselves, which might take a lot of time, it might risk messing things up in a whole bunch of ways, or should they bring it back to the delegator, the manager who set the task? If you do this too often, that's going to waste all of your time as a manager. If people raise exceptions all the time, you give me a £5 budget to buy screwdrivers with, and I found this one that's £3 and this other one is £4, but it's made of a slightly better kind of ABS plastic. Which one should I buy? You don't want to have your time wasted with tiny exceptions like that. But if a delegate is really stuck on something that's going to create 3 months of coding nightmares if they make the wrong design decision, then it is worth coming and raising that. So it's important to be very clear how and when should exceptions be raised, and how are you going to be handling them. Once you give a task out, you've then got to let them get on with it. If you spend your own time micromanaging the task, you've defeated the whole point of having a delegate available to do it for you. You're supposed to spend your own time doing your own tasks, and you have other people to take things off of your list, out of your way, and bring them back when they're finished. So you have to trust people to go off and do it after that. The other major part of scheduling is to do with risk management. Risk management is often done very badly, including by people who are supposed to know about it and portray themselves as experts, but they don't actually understand the fundamental meaning of what risk is. Now, computer scientists can understand this very properly because we study probability theory and statistics and advanced Bayesian methods. So we should have an advantage over most people in that we have better concepts of risk management, and we should be not afraid to bring them out and use them for management approaches. As a proper piece of probabilistic modeling, we should ask for each task, what is our probability distribution, our belief about its duration? Okay, we don't know in advance how long it will take. We have maybe something like a Gaussian belief distribution over how long it will take. We have a similar probability distribution over what this task is going to cost. We may know the utility, so utility, You may wish to measure this in dollars or in happiness tokens or whatever, but what is the value of actually completing the task? And what is the value of time for the task? What's the usually negative utility of a delay in the task? You might have probability distributions over all of these variables as well. So you might not know what the probability of a delay is, but you know how uncertain you are about your own belief in the delay. So you can have quite complex second order probability distributions over all of these variables. So you then have to think about how do these affect the starting date of all the other tasks. So in a dependency diagram, we say X depends on Y. If you're uncertain about when Y is going to finish, that's going to affect your probability distribution, your belief P, over the start date of the next task. So you'll see dependencies will get delayed through this. Some tasks may be brought into play or removed, canned, if certain things happen. So if you have these probabilities and everything turns out to go really quickly on the good side of your time distribution, you might have all these ideas. These are things people have proposed that aren't really necessary, but they're nice to have, and your plan is now going to update as those extra ideas get brought in. Or you might build in some of these optional, sometimes called stretch targets, which are nice to have. They're included in your plan from the beginning, but they're designed so they can be taken out if things are going badly on the bad side of the time distribution. You might have specific tasks in your plan called mitigation tasks. These are tasks which will only be activated if a particular event occurs. If something has gone wrong, you're going to switch usually to a backup plan. For example, classic student project failure is when you say you're going to build a robotics project on a real robot and the robot either breaks or is otherwise unavailable. And so you have this backup plan called a mitigation task. You've planned that in advance. You're going to switch all your work to simulation. You're going to spend some time building a 3D simulation of the robot, and then you're going to make all your existing tasks run on the simulation rather than the real robot. So this is quite a complex model, right? We've got a bunch of tasks over time. Everything has a belief, the start time, the value, and so on. We can have beliefs about the beliefs, which tell us how confident we are. So there's a difference in being absolutely certain that the project has a 50% chance of success and in just not knowing what the probability of success is. Okay, this is the difference between a known unknown and a unknown unknown. So if you have a project where you just don't know the chance of success, you will probably then design a bunch of tasks which are intended to give you more information, and that information will refine your belief about the success chance. If the chance of success is really fixed and you already know that it's 50%, so for example, your project is to build a nuclear bomb that goes off on the flip of a coin, and the bomb will always go off with that 50-50 chance, and it doesn't matter how much extra information you find out, that's the chances of the project outcome. That's a different kind of project from one where you're gathering information and learning about the probabilities as you go. And then you have these other tasks that are going to appear and disappear in response to things that are happening during the project. So this is a complex setup. Again, there are optimal mathematical algorithms, optimal scheduling policies under risk, which apply here. So a policy is a different beast from a plan. A plan is just saying we're going to do X, Y, and Z in this order. A policy is a set of state action pairs. A policy says, here are all the possible states of the world we might end up in, and here is what we will do in every one of those states of the world. So you come across this in AI, especially in reinforcement learning. For example, DeepMind has been training AI systems to play video games based on this approach. They consider what are all the states the video game can be in, the configurations of the characters, and what are the correct actions to take in each of those states. So policy is a much bigger beast than a single plan. And we're searching here for an optimal policy. Of all the different policies that are out there, which is the best one, usually in the sense of maximizing our expected total utility, which in the case of a business is making the most money. So actually solving optimal policy models is very, very hard, and it's one of my research areas. There are several heuristic approximations out there which you'll encounter, and these are only approximations to solving it properly. One of the main ones you'll see typically used by real engineers rather than software people is called the risk register. And in terms of computer science, this is based on fuzzy logic theory. So in fuzzy logic, you take a bunch of numbers that are supposed to be continuous, like probabilities, can range from 0 to 1, any real number between 0 and 1, and you approximate them by discrete categories. So you might create fuzzy probabilities of just low, medium, and high risk to replace the numbers. You can replace the utility functions by fuzzy severities, low, medium, and high. And these are severities both before your mitigations and after your mitigation. Now this is well used by engineers. Computer scientists should be able to do this a little better, I think. As someone who actually studies probability, I'm not happy with low and medium and high risks. I don't know what those mean. I'd much rather see these as numerical probabilities. You have a risk that the robot batteries are going to explode. What actually is that risk? Give me a number on it, and then I can manage it. So maybe you have a 0.75 belief that the batteries will explode. That's the risk. And usually you don't know what that value is. You have a second order belief about the belief. So what I'd really like to see in your project reports, if you like, are standard deviations like this. Say we think the risk of the battery exploding is somewhere between 0.65 and 0.85. Okay, that is a good model of what's actually going on there. And this expresses your confidence in the belief. It gives you the ability to design tasks that will learn more information to refine these estimates. We can do the same thing with the severities or utilities. What does it mean to have a high severity risk? It's better if you tell me the risk of this is $500 plus or minus $100. Now I can actually model it and manage it properly. When we design mitigations for these risks, we don't just want them to be a bit of text in a spreadsheet. We want them to be formal tasks, formal mitigation status tasks in our IT system. We want it to be represented semantically. This is a task that will be activated in a particular situation. That's called a mitigation task. And then you can specify your beliefs and your standard deviations of those beliefs after the mitigation task as well as before it. So another type of approximation you might come across is called a PERT chart. Now, unlike Gantt, this actually stands for something, Performance Evaluation Resource Toolkit, maybe. And a PERT chart is based on a dependency diagram. This is one from a real student project from last year. Or is it this year? Matthew, is this yours? Is this your C natural chart? I see there's some CN down there. Okay, what we've done here is we've extended each of these tasks with an estimate of how long it's going to take. So we've added a expected duration number together with some uncertainty. We're saying what's the minimum length of time, what's the maximum length of time it's likely to take. When we do that, we can use dynamic programming to propagate those estimates across the network, and we can see, for example, distributions on possible start times of tasks based on delays from previous tasks. Again, this is only an approximation. It's not completely solving the schedule problem. So in particular, there's nothing here about values or utilities or mitigation tasks in a PERT chart. To really solve the schedule properly is an active research area, and it's something that I'm involved in, and it's something that Mark from Google was going to come here and tell us about. This is collaboration study we did a few years ago on really trying to do this kind of thing properly. We set up a business management problem. In this case, it's inventory management. So we have a bunch of tasks to do with maintaining stock inventories in food warehouses. And we're trying to decide what are the optimal actions we should take in each state. What is the optimal policy for scheduling these tasks about moving food around and maintaining supplies in warehouses? So here we're using Bayesian network theory. We're using dynamic Bayesian networks. These are the equations for Bayesian networks. Each node specifies a probability distribution conditioned on the state of its parent nodes. We specify a utility function. We consider the average utility, discount it over time, because usually we prefer to have reward now than sometime in the future. We reinforcement learning to iteratively update our best estimates of the policies. This is similar to what is being done at DeepMind, both for simple tasks like playing video games, but then also for real life management tasks. And we can control how much we want to experiment, how much do we care about gathering information to reduce the probabilities versus actually exploiting the information we already have. So I'm not going to go through the details of this. If you're interested, you can check the paper here. But the point I'm trying to make is that optimal scheduling under uncertainty is very complex. It is an active research area. There are proper mathematical methods out there to do it. And when you see things like risk registers and PERT charts, you can view them as approximations to how you'd really do this properly. Maybe one day we will get rid of human schedulers altogether, and we'll just all plug our to-do lists into these IT systems. We'll give everything a priority and a value, and the machine will just tell us what to do every day. We could have an operating system for scheduling human work. Okay, that's scheduling. Another important team skill is coding together. How do you actually make sure your code works well with other people's code? We've talked a lot in this module about interfaces, APIs. An interface can be viewed as a promise, as one of many ways of making contracts. So if we consider an interface as a contract, we're not just talking about the function header, we're talking about any other promises and assertions that are made, both about the inputs and the outputs. Sometimes it's called a code boundary. It's a place where my code stops and your code starts, and we need to agree on what exactly is acceptable to flow in both directions across that boundary. It's not always even done through function headers. There are other ways to specify code interfaces. For example, in the ROS robot operating system, this is all done through the publish subscribe design pattern. We specify the standard messages and the meanings of standard messages. Or you might communicate through file formats. You might say everyone's going to use this certain type of XML to pass across the code boundary. So this is really the main time when people need to physically meet and design and argue and agree on both on the technical end of this, but also on the conceptual issues behind it. What does this boundary actually mean? If we say we're going to pass a cat object into your database, what do we actually mean by a cat? Does a cat have to have 4 legs? Does the database have to support 3-legged cats? Does the database have to support other types of felines like lions and tigers? What exactly is the concept in the real world that is being represented by this software object? So this is one of the few good reasons to have meetings with the whole team. Anyone who's involved with this interface has to understand both the technical end of it, but also the real world semantics that it's supposed to be representing. And you need to define who is the owner of which end of this. We've talked about contracts, we've talked about blame allocation. It's often useful to have a named individual who will own an implementation, and that is the person who you blame. We call this blame allocation. So not necessarily a bad thing. It doesn't mean you're a bad human being if you get blamed, but it means you are the person who promises they're going to look after this. You will fix any bugs or glitches that show up as the work progresses. And if everyone understands what is their role, you can reduce a whole bunch of tensions and arguments there. Now everyone has a nice technical role and you just have to do your technical work, and that helps to make everybody happy once you've made those agreements in the first place. So that's big picture stuff. At the level of code, we have to have coding standards for most languages. A perfect language would not need to do this, because a perfect language would say there is one way of doing everything and that's the standard way and that's what everybody does, off you go. But in most languages, there remains some degrees of freedom about how things are done. So this can be really silly, trivial things like, should we put curly brackets on a new line or on the end of an old line? Famously in the Python community, there's a religious war over tabs versus spaces, which threatens to blow the whole community apart on occasions. I am a tab person. I believe in tabs. I will fight for tabs. Space people are splitters and evil. I prefer hanging around with R programmers than Python space people. Variable naming conventions. You'll see some languages at least recommend certain styles. Famously, Java likes this camel casing. This is where we put in capital letters as part of a long string. Other languages, the C community tends to prefer underscores. Some communities will mix them. Other kinds of variable naming conventions, do you put nouns before verbs or vice versa? So many people like to put the noun followed by an adjective. Like in French, you don't say the red car, you say the car red, because now if you have 3 different cars, when you start typing car, that might help your auto-completion system to tell you what all the different cars are, which has some semantic usefulness. That's more useful than getting a list of red things every time you start typing the word red. There's other conventions. For example, we saw a standard way of notating singletons by putting the word the in front of them. I like this convention where you make multiple plurals. When you have a list of lists, you can notate it by putting extra s's on the end. So I can have a list called my objects, and then if I've got a list of lists, I can call that my objects with a double s. And in some cases, I'll have 4 or 5 s's, indicating how meta the structures become. Many coding standards include these stock phrases, especially in robotics. You're often dealing with a ground truth version of something and a hypothesized or perceptual version of something, and maybe you have a desired version of something. For example, a robot might have a desired location where it's trying to get to. It might have a ground truth location where it is and a hypothesized location where it thinks it is. And so by putting prefixes like des, ground, and hype in front of other variable names, they help other readers to understand what is meant by that variable. So these are very low-level things, but it's important for everyone in the team to use the same standard. Otherwise, they will get very confused, and you'll get into edit wars with people just changing each other's codes to meet the different standards. So at higher levels, more semantic levels, you can all agree on standards for bigger picture stuff in your language. Especially in languages like C, family languages, there are features that are considered dangerous, such as pointers, bit twiddling. These are things which can do very powerful stuff, but they make your code harder to read by other members of the team, and they can introduce possibilities for bugs. So you might have a standard where we all agree we're not going to do any of that stuff. Or we might have a language like Rust, which enforces some of those promises. It says if you're going to do some of that stuff, you have to put it in a special thing, and everyone agrees that they're only going to go in there if they know what they're doing. You can either do that using a language standard or use it as your own internal team social convention. So you might all agree on using certain types of contracts. You might agree on ways of using assert functions to enforce contracts in your code. You might agree on the use of particular linters as well as tests, standard tests that everyone has to pass. Can I just take one moment, please? Sorry, that's the joy of working from home. Right. So, coding standards. So when we get to merging our code together, then everyone's going to go off and work on these different tasks. You're going to delegate work out to different members of the team. Somehow they have to each live in their own little world, and then they're going to come and merge their work together, and it has to still work when you put these things together. So the main way we do this technically is by using feature branches. If you're using a source control system like Git, we are going to typically create a separate branch for each feature. So here's feature 1, here's feature 2. You give that to a team member, they're going to go off and build it, and then you agree maybe on a particular day, maybe on a regular basis, everyone's going to meet up, merge their features together, and make the thing work and get it into a release. So during that merge process, you hope that these features have been designed to be orthogonal, to be independent of each other. But you may have to physically or virtually meet at that point in order to smooth out any issues that arise if people have gone off in different directions with their different features. So you can help this process by using tests. Again, put everything with unit tests around it. When someone goes off to add a feature, make sure they pass the tests by themselves first, and then make sure that when you merge things together, you're still passing the same set of tests. There are many web-based front ends to Git systems out there. These will not only give you a nice backup of your source control system, but they might also provide extra features like issue tracking. This is effectively another version of the to-do list, the scheduling system we saw, but now with links into the source code. So a task can be linked to a particular part of the software that needs to be fixed. You'll see other features like tagging with different themes or features to assign issues to different people. I would recommend GitLab as a nice open source version of this. You can install GitLab on your own server as a piece of open source software. The commercial company GitLab also hosts this on their own servers and provides some extra features for a fee. Okay, so we've done scheduling, we've done coding together. The final team working skill I'm going to talk about is sharing information across the team. So you will often need to write technical documentation, not just to pass exams and keep your managers happy, but to actually communicate information between members of the team. As far as possible, you should try and do this automatically. There are tools which will take your code. Your code is the design. Your code is the ultimate ground truth version of everything you're doing. And if you can generate documentation from the code, you have a much better chance of the documentation being correct than if you try to write it as a separate process. So for example, there are tools like PyReverse, which will take your Python code and turn it into UML diagrams like this, which you can then use to communicate with other members of your team to show them what your architectural software design is looking like. There are tools like Doxygen, which will pull out API descriptors. Doxygen will look for everything that is declared public. It will pull out all the function headers. It will pull out comments associated with the function headers if they're marked as being for public reading. And it will create a nice, both online and paper PDF style version of your program documentation. So for many projects, you can do all the documentation automatically from the code. The code should always be the definitive version of everything. Don't fork your code and your documentation. Have the code as the authoritative source, generate everything from the code. You might sometimes need to write a bit of English text about the really big picture stuff, especially the meanings of concepts. So for example, if everyone's agreed that a cat is a four-legged domestic animal and is not a tiger or a three-legged cat, that kind of thing will need to go here to define what you actually mean in the real world by the classes. You might need English text describing the overall software architecture, especially if you're using design patterns. Clever architectural ideas need to be explained in English. Write everything in LaTeX. LaTeX is a technical documentation system which creates very good documentation, especially for mathematical projects, but also for everything. You can write your novel in LaTeX and it will come out not only looking beautiful but looking very well structured, because LaTeX encourages you to use a logical structure with sections and subsections and references all done correctly. It will do your Harvard referencing automatically for you and ensure that everything is where it should be. For anyone who is writing up a project right now, LaTeX is very easy. It is quite similar to HTML. You write your source file in this human readable markup language. So for example, we tell it this document is an article, we're using some graphics, this is the title, this is the author, this is the abstract, this is the introduction, this is an equation, and so on. And then you compile it using a command like PDF LaTeX with the file name, and it will generate a beautiful PDF like this for you. You can do beautiful equations in it. You can do your references. You make an external file called a BibTeX file, and again, you give a semantic representation of each document in your references, which will be picked up, and you can tell it how to format them. If you want to use Harvard style referencing or whatever, that's all done automatically. To do the references, you have to give the magic words LaTeX, LaTeX, BibTeX, LaTeX. You have to run 4 commands in that order. Nobody knows why anymore. You just do. Another way to communicate with other team members is through comments in your code. Try to use comments in a good way. There are various misuses of comments which can actually make understanding of your code worse. So don't use comments if variable names themselves are better. If you're saying customer.addOrder, this is very obvious we're adding an order to a customer. You don't need a comment saying add order to customer. And it's dangerous to write this comment, because if you ever change this API, if you do refactoring and make it mean something different, now you're risking your comment going out of synchronization with what's actually happening. Instead, you should use comments to explain the overall flow of the code, explain roughly what this whole function is about, what is it doing, and then the code should be self-explanatory after that. So don't write your comments on single lines. You don't need to say add 1 to X if we're very clearly adding 1 to X. And again, this is dangerous because one day you're going to change that code and you're going to add 2 to X, and now the comment and the code is out of synchronization. Don't use comments to comment out old code. Don't use comments to put in meta information like the author name, the license, the date. This is all what source control systems are for. The code should be a concise description of the code, and this other stuff can go in source control. There are standard name tags that everyone uses in comments. So to do, most famously, this is something that needs to be done in the code. You'll also see things like fix me and hack that are there to alert readers what's going on in the code. Some of these are so formalized now that they're picked up by static analysis tools and by graphical code editors. For example, you have tools which will pull out all the hacks and give you a report about what percentage of hacks have been reduced during February. How not to communicate with your team. The dreaded team meeting. Putting all members of a team in a room is usually loathed as a big waste of time. If you are running task scheduling and delegation correctly, you should never need to do this, because everyone has a task list. Everyone knows what they need to do. If you have people reporting to you, you can take those tasks, hold a one-to-one meeting with them, delegate the work to them. They go off and do it, bring it back the next week. When you've done your tasks, you report them to your manager. They go into their task list. There's no need to have all the members of the team physically present to do any of that. So why do team meetings still occur? I can think of 3 reasons. Social, you do need to build trust between team members. Even with remote video conferencing technology, it's very hard to do this. You need people to physically meet to build this emotional connection rather than just transmitting information. Maybe you don't want to have a meeting to do this. Maybe you just want to take everyone to a pub or a restaurant or go and do something fun. You don't need a formal business meeting to do that. Education, as well as delivering the work this week, you often want to perform this extra activity of improving the skills of your team members. You want to share knowledge, not for the purpose of getting this week's work done, but for generally increasing the skills across the team. This is a different activity from doing the work. It's a good investment to make. Everyone needs to keep their skills going. Sharing skills between members of a team is a good way of doing that. A bad reason to do this is for everyone to educate an incompetent manager. You will see incompetent managers hold a team meeting whose only purpose is for everyone in the team to come and teach the manager what it is that they're doing. So a good manager should already know what is being done. A good manager should be able to do all of the tasks on their task list. They just don't have time to do them, and they delegate them to their people. That means that if anyone raises an exception, the manager is able to fix the problem because they do have the skills already to be able to doing it. If you see lots of meetings like this where everyone's reporting status all the time, this is often a sign to run and go and work in a team with a more competent manager. The best reason to hold a meeting, though, is to agree on these shared interfaces. This is really where people have to meet up. Everyone who's involved with using or implementing an interface has to understand what it means, both technically and conceptually. That's where you really do have to meet either physically or virtually. And when you do that, you've got to figure out who makes the decision in these meetings. Are you going to vote for it? Is the manager going to do it single-handedly? How exactly will that work? Is everyone still there? You're very quiet.
Yep, still here, Charles.
Yeah, still there. Okay. Okay, so the practicality of running meetings, and if you really must run a meeting, and this should be a last resort, you should really be doing all this stuff one-to-one and delegating work down that chain of command. If you really must run a meeting, how do we make it as painless as possible for everyone involved? I suggest clearly state the aim of the meeting at the start. What is this meeting actually for? What are the conditions for the meeting to end? When the aim is completed, the meeting ends. Don't just sit around having a meeting for the sake of it. Don't be afraid to stop people talking if they go off topic. People talking about irrelevant things in a meeting is extremely annoying for everyone involved and wastes a vast amount of time and resources. If you add up the money cost of all the people sitting in a meeting, think about what is everyone getting paid per hour. What is the actual cost of this meeting? In some cases, it can be astonishing how much money is wasted in unnecessary meetings. So, for example, you might say the aim of today's meeting is to agree on this API. Let's do that. Anyone starts talking about the weather or whatever, don't be afraid to cut them off. And then when you've agreed on the API, stop the meeting, get back to real work. You need to clearly define and document any decisions. Is the purpose of the meeting to take an action or to agree on what action will be taken? Is the action to specify the API? Has everyone formally agreed that's what it's going to be? So define who has the power to make the decisions. Consider a decision as a formal entity. It should be recorded in your IT system of your choice. Document who voted for it, who voted against it, and everyone should sign it or otherwise agree that this decision was actually taken. You may want to combine many small meetings into one. This is called having an agenda. Think of an agenda as a sequence of small meetings, one after the other. Each is given a time duration. You have to enforce that time duration, stop people talking, get on with the meeting, get everything agreed as you go along. So finally, given the current state of the world, I thought I'd talk about some specific teams for remote working. Increasingly, the world is moving towards this style of working anyway, regardless of COVID-19. This is the direction of travel. Why would you want to have a remote working team rather than a physically co-located team? From a business point of view, you can get better staff. Most human beings aren't completely mobile. Most human beings are embedded in a network, a complex social network of family members and companies, and people act as parents and carers. You can care for your elderly parents, or your not so elderly parents, maybe giving grandparental care to your children. You have a partner, your partner has a job, your job has to be near someone else's job because the businesses have a relationship. We exist in a complex physical social web, and it's usually not possible to just pull someone out of that web and stick them in a different physical location just to do a particular job. But at the same time, work is becoming more and more specialized. So we used to have programmer as a job category. Now you have to be a particular type of programmer. You're a C programmer or a Java programmer, or you do finance, or you do robotics, and things get more and more specialized. And there's a tension between people needing to be the one person in the world who can do a piece of work and where they actually sit in this physical web of relationships, which defines where they're able to go to work with other people. So if you switch to remote working, you can get much better people on your team. You can find the one person in the world, in whatever country they're in, who is the absolute expert in the thing you're doing, and bring them in, even for a temporary project, without having to worry about untangling all these social webs. If you do pull someone out of the social web, you're going to have to pay them a huge amount of money to make it worth their while to relocate. So we now know that remote working staff become 13% more productive. This was done for the first time in a fully controlled large-scale trial as a proper scientific experiment in 2015 by Stanford University. And it's very difficult to run a fully controlled trial. You have to find a company who is willing to experiment by putting half of their staff with even numbered letters in their surname on remote working, and the other half with odd numbered letters in their surname as physical working. That's how you run a proper controlled trial and get rid of all the confounding factors. So it was found by doing this trial over 2 years with 500 people, I think, you get a 13% productivity gain in the remote workers. They're happier, they don't have to spend time commuting, and they tend to spend a significant portion of their commute time doing extra work because they're so happy. They do, however, report they need occasional physical meetings to build trust. So people don't like working entirely remotely. They like to do the actual work remotely and then have these occasional meetings to do the team working stuff. So maybe once every couple of weeks, you have a physical meeting where everyone drives to Lincoln to have their team meeting and go to the pub and do that stuff. And then you all go back to where you live to get the work done. Remote working is good for the planet and for the economy. It reduces traffic, congestion, pollution, carbon emissions. It reduces the load on the NHS from physical and health problems related to commuting. It can help spread out the work around the country. It helps rural areas, which are otherwise less connected to the economy. It's good for your business. You can avoid high rents in city centres by having everyone work from home. You can encourage childcare, local community work. You can encourage all the links in the real physical social networks while still getting this ultra specialization of the work being done around the world. If you're interested in this, I've been working with a bunch of geographers on something called the Future of Rural Mobility Study, which is coming out very soon in 2020. That's where this figure comes from. And finally, as we've been finding in the last couple of weeks, remote working is making our team working and specifically our meetings more efficient than they used to be. When you have a remote meeting like this, you don't waste people's time People can record the meeting, they can step in and out of the meeting. People can have side channel chats if the meeting is not relevant to them. They can discuss with one another. They can share extra information, not just as text, but as links to things on the internet, to videos, to documents. People can log out of the meeting and do some work on their desktop for a while and come back in when the meeting becomes relevant to them again. And remote meetings also tend to discourage micromanagement. They promote this idea that you give a work package to your delegates, they're going to go away and bring it back rather than you standing over them, telling them how to do it the whole time. They discourage presenteeism. That's the culture of just showing up to your office and putting your jacket on the back of your chair and being there rather than actually delivering and being rewarded and monitored for delivery. Gary says, what about 90% of communication is body language, etc.? I think in technical work, it probably isn't. In a technical meeting, you're mostly talking about technical stuff. Probably 10% of communication is body language, which is related to all the trust and social building. And that's the 10% that you do once every 2 weeks when you physically meet up and go to the pub. But I don't need to see your body language if we're just agreeing on a function call for an API. So how to actually do this? I hope a lot of you are already running your group projects through remote team working by now. Some specific technologies I'd like to highlight and to recommend are the Jitsi system. So Jitsi is a great free software implementation of remote video conferencing. You can run Jitsi on your own server, or you can find a commercial host such as 8x8 who sponsor open source development of Jitsi. They can host your video call for you. Now, Jitsi is built on top of WebRTC. WebRTC is a open protocol for one-to-one video calls. No longer need any special software at all to make a one-to-one video call. It's built into a standard API that is part of your browser now. And if you want to create a one-to-one video call on your own website, you can do it in just a few lines of JavaScript, which tell your browser to run WebRTC. What Jitsi is doing is running larger meetings where everyone makes a one-to-one call to the Jitsi server, and Jitsi works to combine all those video feeds together and then send them out again to each of the participants. So you'll get screens like this where you can see everyone together. That is an inherently high performance activity. You need to be running on a fast server to do this. If you're running a big meeting with hundreds of people, your server's going to be doing a lot of work, taking 100 video feeds and merging them together and sending them out again. So you're probably not going to run this on your laptop. You're probably, if you want to run your own install, rent some time on a cloud server for a few pounds a month and install Jitsi over there. But if you just want to hold a meeting right now, go to this website on 8x8, and with a couple of clicks, you can run your team meeting on a fully open source stack. The other way we like to communicate in Teams is through instant messaging, especially integrated with video conferencing now. So in instant messaging, you have a chat room, you have a bunch of users, everyone can post asynchronously, everyone can see the history. It's a great way to have your technical discussions and keep a record of them. The one I would recommend is called Matrix, because again, it is free software and it is federated. That means no one can spy on your data. Everyone running a Matrix server is part of a network. There are copies made of these discussions. Everything's encrypted end to end, so no one is in overall charge of the network. The concept is based on the Git concept of distributed copies of everything. You'll need a client app such as Riot to run on it, and Matrix is nice because it will bridge to everything else. If you've got people on any of these other systems, Discord, Slack, WhatsApp, whatever, you can plug them in and they'll appear on your Matrix system. And you can create a Jitsi video conference inside of your Matrix session. Okay, that's team working skills. We've looked at scheduling, use dependency diagrams, priority queues, do delegation properly, think about proper risk management with probability theory. We've looked at coding standards and coding together in general, how to do branching and merging, give each member of the team a feature branch, merge them together when they're done, make sure everyone passes the tests. And we looked at sharing information. That means technical docs, co-comments, try to avoid meetings wherever possible. Remote working, even before coronavirus happened, remote working was the future anyway. What we're seeing here is just accelerating it.